Greetings. It's an honor to be with you here today. Looking forward to talking about simulations. It has been said that there is no such thing as programming. There is only bugging, followed by debugging. About a year ago, on a beautiful sunny Seattle March afternoon, there we were. Some of us were bugging, the unlucky ones were debugging, and a certain VP, who shall remain nameless, comes walking through the floor asking for volunteers. I need you to be on an iOS phone. Bring your Bluetooth headset. Oh, and be sure you installed the latest version of the app. Oh, and you got to join this feature group before you come. Hurry, everybody. So we all ran down, got our stuff, showed up, and after about 20 minutes of fidgeting around, we were finally testing what it was we were there to test. But we all left saying, there's got to be a better way. And indeed, over the last year, we've spent quite a bit of time trying to find a better way than asking all your coworkers to come help you test your new feature in calling. How did I get to be here? Well, when I was about 15, I learned German. I also gained access to an AT&T 3B2 microcomputer and started learning Linux. I fell in love with everything that came from Kernighan, Pike, Ritchie, all those pioneers at Bell Labs. I loved it so much that I had my name legally changed to Wurzel, which is the German word for root, which means, yes, you are actually looking at a true zero. You is zero, that is. So how did I end up here? Well, I spent about 25 years in startups, and then I kept saying, I'm a hardware guy. I'm never going to work for a company that's more than 200 people. And all of a sudden, 8 years ago, there I was, my first day at Facebook as a software engineer going, how did this happen? Well, I spent a lot of time in codecs, videos, video metrics. And about a year ago, I had a chance to come and work on something new and exciting, which is tooling. Because one of the things that really was different for me between startups and a big company like Facebook is in a startup, you don't have the time or the money to invest in big projects that are there just for the developers or just for the experience. You got to focus on the product. But as you get to a bigger company like Meta, you realize that investing in the tooling and the developer experience helps you improve the products. It's something you can do at a big company, you just can't do at startups. So when I had a chance to move into the RTC calling area and work on developer experience, I jumped at the chance. So what I'd like to talk to you today is the thing we've been working on. Why simulate? Maybe simulation can help us iterate faster. Maybe simulations can help us protect the user experience. I think it did, and I'm going to hopefully show you some of the wins that we got out of working on this area. But simulations is expensive, right? It costs more than running a simple unit test or even a lot of kinds of integration tests. So why would we invest in this area? We saw two main benefits. The first was shifting existing coverage left, and the second was gaining additional areas of coverage. So our team is part of developer experience. Our job is to help developers work faster. That includes user interface developers, codec, backend, network engineers, anyone who needs to do stuff to help their system run better or to help their code run better. We're there to help them do that better. So we do this by shifting our coverage left and adding new coverage. What do I mean by shifting left? Well, there are a lot of challenges when scaling to larger calls. For example, grid view and pagination involved a whole lot of new user interface work. There were a lot of deep dive subjects like simulcast, bandwidth estimation, temporal layers, things that only certain people have expertise in and needed additional work. And finally, the backend systems, signaling and media servers, had to have a lot of work done to help them scale and handle these new kinds of traffic successfully. So let's say we have a bug, right? I want to shift this bug to the left. How do I do it? Well, if you ask me, this is the answer. But I ran that by my manager and he said, I think you're reverting to your hardware guy ways again. So we thought, let's do it like a software guy. Let's look at the software development lifecycle. It starts with developers doing the things that developers do. Looking at problems, looking at algorithms, tuning codecs, writing user interface experiences, functional and load testing, those things that you can do solo. Eventually, you build and deploy that product. And finally, it goes out to the users. Here's the issue. If you find a defect in build and deploy, it can be 2 to 5 times as expensive as discovering that during the development process. And likewise, if you wait until it gets out to your users, it can be 5 to 10 times as expensive beyond that. And it also comes with a lot of risk. on top of the risk to your product and your user experience, there's also a chance that you won't even get good signal on that bug. There will be too much noise in the user reports or too little signal coming back from the logging, and you won't be able to repro that and fix it. So simulations can help with that by moving bug discovery to the left, where it's less expensive and hopefully easier. So there are challenges to RTC. I think it's one of the more challenging areas of software to test. And if you use field trials to do that, you have a huge risk to degrading your user experience. There's issues with reliability of logging, and in some jurisdictions, even legality, you may not be able to get the logs that you need. Reproducibility is a big issue. Something happened out in the field. Can I make that happen back in the lab so that I can understand and learn more about it? And hopefully, the goal would be to get a debugger attached to something while it's failing and see exactly what's going on. And that's simply never going to happen with a bug that's happening out in the field. So we wanted to find a way to run experiments without harming our user experience. The old way was, let's farm a hypothesis. Let's wait until that deploys. Could be a long time, weeks if it's a mobile client. Test it in the field, and then hope. Hope that we didn't ruin our user experience. Hope we got the data we needed. Hope that it moved the direction we wanted it to. Hope. Not a great strategy. So instead, with simulations, we try to move to a different model, which is let's form a hypothesis, and then let's intentionally craft a set of scenarios, a set of conditions, and a set of configurations that we can operate that product within to try to simulate what's going on in the real world in a way that helps us to test those areas that are applicable to this hypothesis. Run that through simulations and evaluate how it did. If this can be done much faster than the old way, we can get that signal back, feed it to the developers, improve or revise our hypothesis, and get working code much sooner. So where does this all fit in the RTC stacks? Well, I'm going to talk about two test frameworks, and here's where they fit in our stuff. In about an hour, you're going to get a talk from Ishan and Hani that's going to be much better talking about the details of this. But just really briefly, we have WebRTC encapsulated in a library that lets us use it across the Facebook family of apps. So what kinds of testing existed before we did simulations? Obviously, we had unit tests. Some of those are included with WebRTC. We also wrote some of our own. There's UI driver tests, where you use Appium to drive the complete app. We had QA testers operating various things. Some of them were client-specific. Some of them were trying to get all those developers to help test back-end server load. And finally, there were cases we had some infrastructure that could lease cloud clients and use those to load test the servers in certain ways. But wouldn't it be really cool if we could simulate a 10-minute call in 1 minute? Let's see how we made that happen. We've made a system called Newton, which helps developers to iterate faster. It's deterministic, and it runs faster than real time. So let's look at a high-level model of how a call works in RTC. There's a camera, which is delivering frames at a regular pace, 30 frames per second, to the RTC stack. There's also a network, which is delivering packets with some amount of delay, some realistic delays happening in that network. As those frames and those packets come in, the CPU has certain amounts of work to do. In a typical call, there's spaces between there where there's no work to be done and the CPU is hopefully sitting idle. What if we could compress all of those together and do that work connected without any of that space? We would help the developer to test faster. This is doable, but there's two keys. You have to keep everything in order, and you have to lie about the timestamps. So how do we achieve this? Well, we start with what looks like a normal RTC test. We have a user endpoint with an implementation of the stack. We have a peer endpoint with an implementation of the stack. And we connect those with network conditioners. The important feature of the network conditioner is that there's a random number generator seed supplied. And based on that seed, all of the delays, all the packet loss, everything it does will be determined by that random number seed. So if we run it again, we'll get the same delays, the same packets lost. That makes it reproducible, but also across different tests, we can vary it by supplying different random number seeds. Below this, we connect all the standard infrastructure that we would supply, including media file upload, configurations, the different network settings that we want to use for different tests. And above it, the most important part, we have a simulated clock and we have task queues, and we make sure that every component in the system is making use of that clock and those task queues. And that lets us make sure that everything goes in the same order and that everything thinks that it had the same amount of delay, whether it really did or not. We also wrap this with a bunch of scripts that make it really easy for a developer to launch 5,000, 10,000, 20,000 calls, whatever they need, and to combinationally group the configuration and the product configuration and the network configuration so they can test all different combinations. All those tests run, and then we gather all the results back together, and we can do two things. We can aggregate them and look at how that experiment changed the averages for different metrics, but we can also find outliers. If there was one run where the algorithm went off the rails or the tuning parameters weren't great and it did something pathological, we can find the random number for that seed, random number seed for that run, bring that back and reproduce that exact same run locally with a debugger attached. So it gets us the benefits of scale while also letting us put a particular problem under a microscope and see what happened with it. So that's Newton, and later I'm going to talk about some of the wins that we got from this. But I did want to show some sample output. We try to give the developer immediate feedback by bringing up results from their runs immediately in a graphical window. And we also log all that data into the standard data pipeline so it can be analyzed with the traditional tools in notebooks or add alerts to it, look at historical data, how this experiment changed versus others. So that's an example of a system that pushed things down almost to the level of a unit test. It's using unit test infrastructure and gave us huge value. Now let's go the other direction and still help shift things to the left by building large systems. So the thing we built to do this is called Collagen because it generates calls. We use this to protect user experience. It does it using real clients running in real time on real networks. We lost the benefit of non-determinism. That's a great thing about Newton. If you put a real network in there, you're not going to be able to reproduce exact same scenarios. But the benefits we get are it's full stack. So we do get to test as much of the stack as we want to, including the back-end server areas that Newton does not touch. And even though we're using not exactly reproducible network conditions, we can still tailor them. And we can also make the individual automated participants or bots do things on exactly the same time scale. So it's more reproducible than using human QA to do these same tests. It's also more scalable. We look at Collagen not just as an orchestrator for running bots, but as an overall developer experience. We want to make it easier for people to author, execute, and analyze. So authoring consists of making up a simulation plan. How many participants do I want? What do they do when? What are the network conditions that they're operating under? All of that is easily configurable by the developer per test, or they can use a library of pre-existing test configurations. They can also supply custom media files. Then they pass it into Collagen, and the execution engine takes over. The controller has access to a pool of workers. Those workers take on individual roles in the call, and they can use local headless clients, or they can fork out to actual hardware labs and lease individual physical phones if that's the kind of test that wants to be done. We also have monitoring and performance over this entire experience so that we know whether the bots did what they were asked when they were asked to. And then finally, if the execution ran successfully, we can then analyze the actual metrics results. If the execution didn't succeed, there's no reason to look at the metrics because they're going to be misleading. But if all the bots did what they were supposed to, all the calls proceeded as expected, then metrics like packet loss, delay, those kinds of things are going to be meaningful in those logged metrics. We also, on a system like this, can take the input video and the output video, or the input audio and the output audio, and feed those back into a quality check and see what the actual impact was on video quality. So we designed a great UI for Collagen. We tried to make it super easy for people to use. It's drag and drop to add events. There's libraries of network scenarios and media files that you can add to your scenario. It's easy to add multiple cohorts of participants that behave differently in a given call. We tried to make it so there was no reason, no delay. You want to simulate? Go for it. We make that easy. Next, we want to communicate in real time how your simulation is progressing. Because once I kick off 10,000 calls, I want to know, are they running? Are they running? I'm a very impatient person. So we give you a feedback where the developer can see how the calls are progressing. And if some of the early ones fail, they can even start to drill into those while the rest of the calls are still running. We make it easy to get all the way from did the overall simulation proceed to how did an individual call to go to how was this particular bot's experience to the internal logging that came from the client libraries running on that bot. We can easily click through that and get any level of information that's needed. And then finally, we take all those metrics that are coming out, production metrics, any additional metrics that the developer added to that particular build to help test the thing they're trying to test. We make them available as much as possible in UIs immediately, and everything goes into pipelines so they can be analyzed in notebooks, alerts, monitoring, comparing day to day, all the things that are useful to do with that data. So RTC at Meta has some particular challenges because we don't just have one app across multiple platforms. We have many apps across multiple platforms, including cases where they have to interoperate. And that makes things extra challenging. So how do we deal with that? Well, we started by defining a single bot harness interface. It's an API that says, I want you to join this call now. I want you to turn your audio on. I want you to turn your video off. I want you to leave the call. Any action that a user can take from the user interface on a call, these bots have commands that can tell them to take that same action at a specific timestamp. Our simplest client takes that API and wires it into a headless version of that RSys stack. We made it headless because that way we don't have to worry about UI changes. When the harness gets a call to join a call, it simply tells the interface, join the call, and we know because it's an RPC call that will happen at the time that we ask for it. On the other hand, sometimes you do want to exercise a new user interface, and so for those, we can plumb that same API into a user interface driver like Appium and command the complete app, either in an emulator or on a physical device. We even go so far as to run web clients. So the advantage for the developer is they can write a simulation plan and a set of configurations and apply those consistently across any different level of simulation across multiple clients and get signal on how it does on multiple platforms with no additional time required from the developer. What were some of the keys to success to making this work? The first is your test configurations have to be representative. If you're working on low bandwidth scenarios, you can't test things with unlimited bandwidth. If you're trying to develop with packet loss, you need to make sure the network conditioner is configured for that. If you're developing a new feature, then your product configuration has to have that feature enabled in those specific clients or for those particular test users. The next one is you have to figure out how many runs are required. For some metrics, it's easy. Maybe 10 or 100 runs is enough. Others might have less of a signal to noise ratio, and you might need 10,000 runs to get something that's statistically significant. So being able to test certain features in Newton first, which is much less expensive, get the early signal with 100,000 calls, and then do an additional 5,000 calls in Collagen gives us a way to scale up our effort as we get more confidence in a particular change or feature. You also need to validate the outputted metrics versus reality. Your simulations may give you some idea that a metric is going to move in a certain direction. That can increase your confidence to send it out to the field. But at some point, you need to feed back in what actually happened in the field back into your system so that you improve it and have higher confidence for future features when they come out. And finally, make it really easy for the developers. This is something we're working on now. When a developer has a new feature, they should be able to say, I want to test this new feature in a library of scenarios, and Collagen should take over and just make that happen and give them a super easy report. Here's A, here's B, here's the differences. So let's look at some of the use cases that we worked on using simulations tooling. The first one, as mentioned earlier, was large calls. Large calls involve work throughout our stack. User interface developers were able to use Collagen to experience what it's like to be in a call with 50 or 60 or 70 other people without having to find people to make that call. They can do it in seconds from their desktop. Media developers were able to use both Newton and Collagen to test improvements to codecs and algorithms and signaling. And back-end engineers have been able to use it to load test and to exercise certain features like screen sharing or having multiple people join and leave a call at once. So it's found uses throughout the stack, which has been fun to see. Another one is Collagen monitors tens or hundreds of thousands of calls per day across a number of different scenarios and client revisions, so we can actually get early signal on when there might be a real problem in production. In this case, there was a very, very infrequent application deadlock. We were just getting some signal that it was happening out in the field, but we were also getting signal that it was happening in Collagen. And that was really cool. What it let us do was repro and start to narrow down the conditions under which this deadlock happened. And then when a fix was available, we were able to validate the fix in simulation before sending it out into the field. As we keep working on this, we expect to be able to do more and more about finding bugs that people weren't even expecting simply from the results of us running so many calls per day in a simulated environment. And finally, a huge thing we just did recently was source code bisect. So source code bisect is a way to use your source code tool to help you identify the specific version that has caused a problem. Your source code control system gives you a version number. You take that version number and build that version of your product. Then write a sim plan and figure out what kinds of network conditions or what kinds of product configurations do I need to try to trigger this bug that I'm looking for. Now, you might say, wait. Why are we using simulations here? Why not just write a unit test that finds that bug? And the answer is because sometimes it's not a binary outcome. There obviously are cases where the test passes or fails, but we might be looking for something where it's a small metrics change. Maybe on an individual call, it can vary by 5 or 10%, but in the aggregate, a particular feature causes a 2% decrease. That's not going to work well with your bisecting system. It's just going to pop randomly around your vision history and really give you back garbage. But if we can run hundreds or thousands of calls with this version and then take the bot clients, have them execute that faithfully, reliably, ensure that they're consistently executing the plan they were asked to, log metrics from that, aggregate those, look at the averages, and feed that back into the source bisect, we can actually find issues through this loop that would have been impossible without being able to run massive numbers of calls and look at aggregates. Does it work? You bet it does. This was a huge win. We had a bug that was very difficult to find. It was hard to tell exactly when it happened in production because we have parallel release trains of feature changes and configuration changes. And so trying to narrow it down to a particular one was very difficult. But by locking in the configuration and then letting HG Bisect do its work to identify which product version was triggered, we were able to see a very distinct outcome in this history, as you can see. So what have we learned from all this? Well, I believe that there is a large and fruitful space in between unit tests and Appium or human QA, where there's a lot of value that can be extracted by finding the right kinds of testing frameworks. We've proven that simulations can definitely save developers a lot of time. We've also shown that automation expands your coverage exponentially rather than linearly. By being able to run tens or hundreds of thousands of runs with combinations of different network and product configurations, we can find corner cases that might not be exposed by just running one test on one configuration over and over. And finally, simulation lets you set up an intentional environment that is also realistic. You can choose what area you want to focus on and get data that is still meaningful for users that are like that kind of scenario out in the real world. So, want to try this yourself? I highly encourage it. First step, look at your ecosystem. What do you have today? What areas have good coverage? What areas are maybe not as well covered? Where are you spending the most resources in terms of development time? Where are the friction points? Are there any gaps in all this where simulations might be able to help? And then consider how you can focus your testing on just specific layers or specific areas of your code base. You don't need to test the whole product. You might be able to get signal by only testing the 10% that's really involved in that particular kind of a bug that you're looking for. And finally, start small. What I've shown you here was the work of many, many people over the course of a year, but we didn't start that way. So find little areas that you can work on, add tooling to help make your developers' lives better, and then hopefully you can spend less time debugging and more time bugging. Well, I would love to stay here and chat with you quite a bit more about this, but I got to go join a call with 42 of my closest friends.